this is a lesson on vector components. Before we actually talk about what vector components means, we need to be able to express direction accurately. So, for example, we've been used to, in this course, using north, south, east, west, right? We know very well north, south, east, west. So if we have vectors acting in those directions, we know what that means. What about, however, if we have a vector that acts in, say, this direction, right? It's not on north, south, east, west. It's sort of between. Well, we could try doing something like this, right? About northeast, it's very close to northeast. And actually between east and northeast, we have east-northeast. So it looks like it's actually like going in that east-northeast direction. So that's one way to do it. And that's the way it's done sort of on maps. But again, that's not very accurate. What if it's between these two, right? What if the direction is between those two? So the way we have, the mathematical way we have to describe direction is with angles. And that's what we're sort of going to stick with in this course. Now, this method here, where we have north as 0 degrees, or I guess technically you could call north 360 degrees too, right? All the way around the circle. Where east is 90 degrees, south is 180 degrees, west is 270 degrees. So for example, if we have something like that, a direction that's like that, we would say that has a bearing of 60 degrees. And it's sort of just understood that the bearing is always the angle from north in a clockwise fashion. So if we say it has a bearing of 240 degrees, we basically know we're going in this direction. Or if we have a bearing of 300 degrees, we're going in this direction. So bearing is just sort of the angle from north clockwise around the circle. That's one way to do it. In this course, though, we're going to use sort of a slight modification on that to make it a little bit easier to visualize. Because if I'm picturing like 310 degrees, it's a little bit tricky in my head to see exactly where that is. So instead, we use this over here as our reference, north, south, east, west. And what we do is we actually, so for example, say we want to find something that's going in this direction, right? We want to describe that direction. What we actually do is we look at the angle that makes with the north, south, east, or west. So we know this is north, south, west, east. We look at the angle it makes with east in this case. And say that's like a 20-degree angle. We would describe that. There's actually a few ways to describe it. One way to describe that would be, the direction would be east 20 degrees north. And what this means is you start off by going east, and then you sort of rotate 20 degrees in the north direction, right? And that makes sense. Another way you sometimes see this is 20 degrees north of east, right? Because it's like you're starting at east and you're going 20 degrees north of east. So you can see either one of these. I actually prefer this one. This is the one I'm going to be using mostly, but you might see this in your textbook problems. Okay, let's actually pause there and do some example problems. So I'm going to leave that at the top so we can see that. So as an example here, we have a vector, a displacement vector, that goes 25 meters. So it's like the distance is 25 meters, and the direction is 30 degrees, sort of between east and north, or from east, I should say, in a northward direction. How would we describe that vector? Well, we would describe it like this. So we would say delta D, with the arrow on top, is equal to 25 meters, and then we put the direction in square brackets. Always, that indicates a direction. You know that from just working with north, south, east, and west. But the direction here, we would say we're starting at east, and we're going 30 degrees north, right? It's like we're starting at east here, and we're going 30 degrees north. That's what's given. All right, see if you can try the second one. Pause the video here, see if you can describe that vector, see if you can figure out what it is. Okay, coming back. You should have tried it already. So this force vector is 10 newtons, and the direction of that is, well, it starts by going west, and then it goes 40 degrees south. So we would say west 40 degrees south because it starts by going in a west direction, and then it's like going 40 degrees in a south direction. And oh, by the way, just to show you, magnitude here, just to refresh your memory on this, magnitude refers to the number or like the length of that vector. The direction refers to obviously the direction of that vector, but magnitude is the word for the distance part or the length of that vector. Okay, last example. Again, try this one yourself before watching me do the solution. So this is a velocity vector. So it's basically the speed and direction that somebody's traveling. So it's 18 meters per second. And if we want to describe the direction is, well, it's like we start at south and we're going 15 degrees to the east. Right? Now, this is a big tip for this course. To make the math easier, whenever we have a vector that's a direction that's from south or north, we should always switch it to being from east or west. Just bear with me for a second. So instead of using the 15 degrees, what's this angle here? Well, we know they would add up to 90 degrees. They're complementary angles. So 90 minus 15, this angle here would be 75 degrees, right? We could also describe this vector v as 18 meters per second, east 75 degrees south, right? Those two things are equivalent. Those two directions are equivalent, right? One is starting from east and going towards the south, 75 degrees. One is starting from south and going towards the east, 15 degrees. They are the same direction. But in this course, to make our math easier for the next lesson, let's always try to get the direction from east or west. So east or west should be the first thing coming up. So when you're not given the direction from east or west, when you're given it from north or south, just switch it. I promise you this will make your life easier in the next lesson. This one isn't technically wrong. It's just this one, is going to make it easier. You'll see why. Okay. This is doing the opposite thing. So let's just quickly sketch these vectors. So if we have a force F1 called F1, these should all have arrows on top of them, by the way. F1 is 20 newtons east, 25 south. So first of all, what direction is that? Let's think about it. I'm going to actually just draw a quick compass here. Ooh, that was messy. Quick compass here like that. We know this is north, south, west, east. And our answer, we know it's going to be east 25 degrees south. So it's starting at the east, right? Starting at the east, and then we rotate sort of 25 degrees south. So it's going to be in this direction here, where this angle is 25 degrees. And we can label that vector. This is F1 is 20 newtons east, 25 degrees south. You're going to run out of space for these other ones. So for this one, for example, you don't necessarily need to draw this compass every time if you can sort of picture it in your head. So this is north 80 degrees west. So if we're starting at north and we're going 80 degrees west, you can sort of picture it. It's almost 90 degrees, almost west. It's very close to west. Actually, let me draw it. Let me actually draw it a little bit better. We're almost going west, so it's like a very steep angle like that, or a very shallow angle, I should say, like that. And if I wanted to draw the angle here from north would be 80 degrees, right? And I'm not going to label it there because basically it's right there. But that is that direction. The length of it would be 1.15 meters per second squared. So this would be an acceleration vector in that direction. And then lastly, delta D, 1,200 kilometers. So this is a displacement again. East 45 degrees north. So think about you're starting at east and you're going 45 degrees to the north. It's going to be a vector that's in that direction. Its length, 1,200 kilometers. And again, there's the label. I don't need to label it because it's there, as long as you can draw the arrow in the right direction. So now we can talk about components, which is what this lesson was supposed to be about. Components refers to the x and the y part of a vector. We talked about this briefly when we talked about work and how work and displacement need to be parallel, or sorry, force and displacement need to be parallel for work to happen. And if it's not, we need to calculate the component of work in the direction of the displacement. So say we have a vector delta D right here. We have this vector. It's not a vector that goes north, south, east, or west. It's like on an angle to one of those directions. Basically, we want to be able to find the part of that vector that goes in the x direction and the part of the vector that goes in the y direction, right? Or in other words, how do we get from this point to this point by only going in the x and the y directions? We could go like that. We also could go, instead of going, we can go up and over, and those are the same things essentially. Usually we like to do x before y though, because, you know, in math we like to do x before y. So the components of a vector are the sort of the x and the y part of it. Now the question is, how can we calculate what the x and the y part of that vector are? And using a little bit of trigonometry, if you know the angle theta, we call the angle theta, if we know the angle and we know the length of this vector, we should be able to find the x and the y component of it. So looking at this as a triangle, a right angle triangle, which is what it is, because the x, we know the x and the y components are going to be perpendicular to each other. X and y axis are perpendicular to each other. So what is the length of this x component here? And we call it delta dx. It's so the whole vector is delta d, and this is the part of it that's in the x direction, so delta dx. So how would we calculate that? I'm just going to do this off to the side. Feel free to copy this down if you want, or if you're already comfortable with it, don't worry about it. But if I'm looking at this, I have this length, and I need to find this length, which of the trig ratios am I going to use? Well, the one that has the adjacent in it, this angle would be, or sorry, this would be the adjacent side, and this would be the hypotenuse, right? So we would use cos. So cos theta is equal to opposite over hypotenuse. In this case, that would be delta dx over our vector, delta d. I'm not going to put the arrow on top of it because it's just the length of that vector we need. We don't actually need the direction here. That's taken care of with the theta. So if we were to rearrange this for delta dx, or the x component, this would just be delta d cos theta, right? If we just cross multiply. So that would be our x component, is just the length of this times cos theta would give us this length. And if we want to find the y component, instead of using cos, we're going to use sine because this is opposite, right? So sine theta equals delta dy over delta d, right? It's opposite over hypotenuse. And if we rearrange that, delta dy is equal to delta d times sine theta. So there we go. We have the x and the y component. We can calculate the x and the y component of this vector. So I just talked about why it's always good to have the angle from the x, or sorry, I should say the angle from east or west, right? I said that on the previous page. Always try to get your angle in terms of, you know, the angle from east or west, not the angle from north or south. And the reason for that is because if we do that, the x component is always going to be the adjacent side, right? If we had the angle from the y, the x component would be the sine, right? We would have to use sine. But if we keep the x component, or sorry, the angle as the one from the east or west, this is always going to be true, that the x component is the length of the vector times cos of the angle from the east or west. And same thing with sine. That only works as long as we're taking the angle from the east or west. So I'm going to put that down. So delta dx in general, our x component is going to be delta d, oops, I wanted to do that in blue, delta d cos theta, and delta dy is delta d sine theta, which is what we just proved. This is only true, I'm going to put a little star, if theta is from east or west. Okay? If it's not, you have to draw the triangle or just use the opposite one. You'll see what I mean when we do a few examples. Moving down here. Okay, so let's calculate the x and the y components of each of the following vectors. And we should also sketch them just so we're used to doing that. So here's a vector d1, 40 meters east, 20 degrees north. So if we were to draw the components, we can draw the x direction of the component and the y direction of the component. The y component of the vector and the x component of the vector. So the way we would label this is if this is delta d1, that's what we're calling this vector with the arrow on top, should have an arrow on top. This would be delta d1x, so it's the x component of that vector. And this would be delta d1y. Okay? So how do we find those values? Well, we know the angle to east 20 degrees north. So is that the right angle? Do we have that angle? Is it this angle here or this angle here? Well, if we think about it for a second, east, so we start by going east, and then we go 20 degrees north, right? So that makes sense that this is the 20 degrees here. So when we calculate the x and the y component, I'm going to do it off to the side here, we can do delta d1x is going to be, well, it's going to be the cosine, right? Because it's the adjacent side to that. So it's going to be basically 40 meters times cos 20 degrees, which comes out to 37.59. I'm going to round this to two significant figures just to keep the question simple. 38. So about 38 meters. That's our x component there. Our delta dy is 40 meters sine 20 degrees. I actually meant to do this in red. I usually, just to make it easier to see the x and the y parts, I'll do the y in red and the x in blue. So anyways, if we do this calculation, 40 sine 20, quickly on a calculator, we get about 14. Just rounding to two significant meters, it's 14 meters. So that's the length of the x part of the component. Sorry, the x component of the vector, and the y component of the vector is 14. At this point, when I've calculated the components, I always like to double check. Does it make sense which one is bigger? Well, if I look at my sketch, it looks like the x component should be bigger because the angle is pretty small here, right? And lo and behold, you see that it's 38 meters, which is bigger than the 14 meters here. So basically, these two vectors combine to give us this vector that's 40 meters long. Now this is good. We found our x and y components. How do we express our final answer? And there's lots of different ways to do this. The way that I like to do it, it's just a nice organization method that we're going to use, is to express the vector with our x and our y components like this. Yeah, I'll stick with red. With the square brackets, a big square brackets, and we put our x component on top, 38 meters, and we put our y component on the bottom, 14 meters. And then we close our square brackets. So the way I've expressed it here is this is the x component and this is the y component. This is called a matrix. And it's just a way of organizing numbers, essentially. That's all a matrix is. So always x comes first and then y comes second. So this is basically just these numbers written in that matrix form. And that's our final answer. So it's always a good idea to express it like that. It's just a very clear way of describing the vectors without a lot of clutter and stuff like that. Okay, so now it's your time to try 2. Your turn to try 2. Try D2, try to find the x and the y components, express them in that matrix form like this at the end. You don't have to use different colors, obviously, but express them in that final form like that. Pause the video here, try it, and then unpause it to see the answer. Okay, there's the answer. So the x component was 60 cos 35, the y component was 60 sine 35. And this is what it looks like in matrix form. Notice how I actually took the m out of the matrix, the unit out of the matrix, which is absolutely fine because the m applies to both of these. This is 49 meters in the x direction, 34 meters in the y direction. Okay, so this one, we'll do it very quickly. Here we have the x component. The angle we're given is west 30 degrees north. So that 30 degrees is going to be there, right? Because west, we go west and then north. So that's the 30 degrees. We know that this is 40 meters. and we can find our x and our y components. Super simple. So the x component, so delta d3x is going to be 40 meters cos 30 degrees, right? Because cos is the x component. In this case, it's the adjacent side, which comes out to 40 cos 30, comes out to about 35 meters. And the y component, delta d3y, is 40 sine 30 degrees, which would come out to 40 sine 30. Oh, I should know that one. It's 20 meters. It's half of, because sine of 30 is 1/2. Anyways, so one thing that's a little bit different about this question. Look at the direction of the components. How are they different than the previous ones? Well, if you notice, in both these previous ones, the x component both went to the right. We consider that a positive direction when we're looking at sort of our regular xy axis, right? If we think about all this stuff taking place on a regular y and x axis, those are the positive axes, right? If we're going this way, we're going negative. So we do the same thing when we use vector components. When we go to the left, we say that that x component is negative. When we go downwards, we say that that y component is negative, right? Otherwise, there's no way to differentiate if we're going to the left or the right. So here, for this question, we actually have to realize that the 35 meters is to the left, right? Which makes this actually, our x component, a negative number. So you have to manually put in that negative number when we either go left or down. So the answer for this one, the components, are negative 35 and 20 meters. Okay, without that negative, we'd never know that it's going to the left. We could assume that it's going to the right. Okay, so last one, we'll just do the last one together. It's pretty quick. 20 meters west, if it's just like that, well, what are the x and the y components of that? Do I even need to do any calculation here? Well, the x component, remember that's going in the x direction. This whole thing seems to be going in the x direction, right? And it specifically has a length of negative 20 in the x direction. Does it go in the y direction at all? Does it go up or down at all? No. So the y component of this is 0. So that is our answer for D4. Just one thing to note. For all these questions, notice how when I put the final answer, I put that this equals this. That the vector here, 40 meters east, 20 degrees north, is equal to the x component being 38 and the y component being 14. And that's true. These are just two different ways to write the same vector. All the information in here is also in here, right? Because this describes the direction by showing you the x and the y part. So just note that a vector written like this is equivalent to its components added up, right? This vector and this vector. So keep that in mind. All right, moving on. Example 3. Let's just do the first one together, and then I'm going to let you try the other two yourself. So this is a vector. It looks like a velocity vector with an x because it's v. It's got an x and a y component. It is a vector because it's got an x and a y component, so the direction matters, right? If it was speed, it wouldn't have an x and a y component. It's got to be velocity. And note also how we don't put the arrows over the components because the components are just like in one direction. Anyways, this is a vector that has an x component of 10 and a y component of 2. So we could write this, if we use our matrix notation, as 10, 2 meters per second. Right? Our x component being 10 and our y component being 2. What would this vector look like? Well, if it goes 10 in the x direction and 2 in the y direction, the positive y direction, right? The resultant vector is going to go from the beginning to the end of that, right? We know that this is 10. We know that this is 2. So the question is, how can we determine the vector? And what I mean by determine the vector, I mean, what's the direction and magnitude of this vector? So what we need to know the length of that vector, and we also need to know the angle, theta. How can we do that? Well, first of all, to find the length, you should be able to see that this is a right angle triangle, right? How do we find the longest side in the right angle triangle? The hypotenuse. We can use the Pythagorean theorem, right? So v squared, or just v, is equal to the square root of 2 squared plus 10 squared, which comes out to, actually I'm just going to do it on the same line, which, super quick calculation, the square root of 4 plus 100 basically is 10.2 meters per second, right? So that's our length of that line. And then how do we find theta? Well, when we find theta, when we have a triangle, we need to find theta. You might remember you're using tan inverse, right? Because we have opposite over adjacent, or we have opposite and adjacent. So it's going to be tan inverse of opposite over adjacent. The opposite will be 2. The adjacent will be 10. So we're dividing. So tan inverse of 2 over 10, tan inverse of 2 over 10, just doing it on my calculator, is 11.3 degrees. Let's just put that 11.3 degrees. Now, how do we write out this final answer like all the previous questions with the magnitude and direction? Well, we can say v is equal to the length of it, which is 10.2 meters per second, and then the direction. If we think about the direction, this is in an east direction, right? So it's going to be east, and then the theta goes north, right? It goes upwards. So we would say 11.3 degrees north. There we go. And now we've basically found that vector based on its components. So I would recommend try the next 2 questions yourself. See if you can figure them out. Pause the video here. When you unpause, it's just going to the answers are going to show up for them. So it's really important that you try them yourself before unpausing the video. Okay, pause it now. Okay, here are the answers. Careful with the direction. Remember, the positive directions are up and right. So this is the positive x direction. This is the positive y direction. So when in this one we have a x component of negative 20, it's got to go to the left by 20. And the y component's positive, so it goes up 6. You use your Pythagorean theorem to find the length. You use inverse tan to find the angle, opposite over adjacent, and you get your answer. Same thing with the last one. This is a sum of forces, so this is a force vector. So these are both negative components. So the x component's got to go to the left, which is the negative direction for x. The y component's got to go down, which is the negative component for down. You might notice that when I did the calculation, I didn't include them as negative numbers for either of them. And that's because when I draw the arrow going in that direction, I only really care about the length of it. The direction of the arrow takes care of that negative for me. So if I also made that a negative 1200, I'd be like double including that negative. Also notice how plugging a negative into this equation doesn't change anything, right? But it does sort of mess up your tan if you start putting negatives in there. So think of it just as a triangle, right? And you don't want to have negative lengths on your triangle, right? You just want to know the length of it. You don't really care about it. So as long as you draw the arrow going in the right direction, you can then figure out the theta, and then once you have theta, like the measure of it, you can figure out the direction. So in this case, it's west 34.7 degrees south, which is the answer.